he did his PhD in 2007 with Sir Popa at UCLA. Since then, he's earned many prizes, the EMS prize in 2012. He's had Bourbaki seminars on his work. He's won many fellowships and awards like the NSF Career Award, the Sloan Award, and most recently, he gave an ICM address in 2018. And his work focuses on the Neumann algebras, group theory, logic, ergodic theory, really tons of things. And anyway, thanks so much for being here today to give our colloquium.
Thank you, Dave, for the very nice introduction, and thank you for inviting me to speak here. And thanks to everyone for attending. So let me start by sharing my screen. So let's see, maybe I'll start by checking that you can all see my screen. Yeah? Can everyone see my screen? All right. Yeah, so the plan of my talk is to tell you about some of the recent work in the area of classification for group von Neumann algebras. And just to make sure we're all on the same page, I'm going to start with an introduction to, well, von Neumann algebras, but even before that, by recalling a few facts about bounded operators on a Hilbert space. So, the typical setup here is H is a Hilbert space. For instance, little L2 of Z, L2 of a measure space. And B of H is the algebra of all bounded operators on H. These are operators whose norm is finite. And the adjoint of an operator always exists for a bounded operator T and satisfies this relation. So, so B of H is an algebra which comes with an adjoint operation. And an operator T in B of H is called self-adjoint if it's equal to its adjoint. So for instance, you can take the multiplication operator on L2 of X coming from a real valued function f in L infinity of X. Okay, so those are all self-adjoint operators. And then an operator is a unitary if T star T is equal to T star, and they're both the identity. So for instance, you can take the shift operator on L2 of Z, which takes the Dirac mass at n to the Dirac mass at n plus 1. So here and after in my talk, I will denote by delta of X to be the orthonormal basis of little L2 of X consisting of the Dirac functions. All right. So this is the basic setup of operators on Hilbert space. So what about the Neumann algebras? Well, B of H is an algebra with an adjoint that comes with at least a couple of natural topologies. The first one was implicit on the previous slide, is the norm topology, where Ti goes to T if the norm of the difference goes to 0. But there's also the weak operator topology. So this is the topology of pointwise convergence of matrix coefficients, if you want. So Ti xi dot eta should go to T of xi dot eta for any pair of vectors xi and eta in the Hilbert space. And a von Neumann algebra is an algebra of bounded operators on H, which is closed under adjoint. So if T belongs to the von Neumann algebra, so does its adjoint. And it's also closed in the weak operator topology. So it's in particular closed in the norm topology, but much more than that is closing under weak limits as well. All right, so let me go ahead and give you some basic examples of von Neumann algebras. So B of H itself is a von Neumann algebra. It's closed by definition. So in particular, if H is finite dimensional, then all matrix algebras are von Neumann algebras. And the same is true for any direct sum of matrix algebras. So the sum of, say, a finite sum of matrix algebras is a von Neumann algebra, and in fact, this describes all finite dimensional von Neumann algebras. Another example is given by L infinity algebras coming from standard measure spaces. So if X mu is a measure space, then you can represent L infinity of x as multiplication operators on L2 of x. And in this way, you realize L infinity of x as a Van Neumann algebra of operators. All right, the other example is that of the commutant. So the commutant denoted by A prime of any set of operators in B of H that's closed under adjoint is a Van Neumann algebra. So here, A prime denotes all the operators in B of H that commute with every operator in A. And again, this may seem like a nice construction of Van Neumann algebras, but it turns out that this is the generic construction by a theorem of Van Neumann from 1929. If M is the Van Neumann algebra, which contains the identity, then M is equal to its double commutant. So it's equal to the commutant of its commutant. So in particular, any Van Neumann algebra is a commutant of something. Okay, so so this gives you a few basic examples of Van Neumann algebras, matrix algebras, more generally B of H, L infinity of x, and then this general construction through commutants. So I'll now move on to constructions of Van Neumann algebras that come from groups and their actions, and this will be at the center of my talk. There's two constructions due to Murray and Van Neumann from the original papers in the 1930s and 1940s. So if gamma is a countable discrete group, then you can build a group Van Neumann algebra L of gamma. And this is generated by the left regular representation of gamma. So what is the left regular representation of gamma? For every group element G, you have a unitary UG on the Hilbert space little L2 of gamma of L2 summable complex valued functions on gamma, which on the Dirac mass at H is the Dirac mass at G times H. So this is really the representation of the group that you get from the left multiplication action of the group on itself. All right, and then L of gamma is defined as the weak operator closure of the span of all these UGs. Well, the UGs form a group, so their span is an algebra, and in fact, it's a copy of the group algebra C of gamma. So L of gamma is the weak operator closure of C of gamma realized as an algebra of operators on L2. Okay, so this is the group Van Neumann algebra, and similarly, if you start with a measure preserving action of a countable group on a probability space X mu, you can build what's called the group measure space Van Neumann algebra L infinity of X cross gamma. So I won't spend much time on this, but let me just say that this one is generated by a copy of L infinity of X and a copy of the group gamma. And you see from the notation that this is a semi-direct product construction. So L infinity of X plays the role of the normal subgroup. So it's a normal subalgebra here. And gamma is a group that normalizes, is a group of unitaries that normalizes L infinity of X. And specifically, if you take a function in L infinity of X and you conjugate it with UG, then you get F composed with multiplication by G inverse. So the group gamma acts on L infinity of X and really implements through this action, the action of gamma on X. All right, so these two classes of algebras both have a key feature, and that is of having a trace. So they admit linear functionals that satisfy that the trace of xy is the same as the trace of yx. So for instance, the trace on L of gamma is given by trace of UG is 1, exactly when G is the identity and is 0 otherwise. This is actually a quite important property for L of gamma. It can be used, for instance, to define a dimension theory for modules over L of gamma, and it was used in the past to define L2 Betty numbers for manifolds and groups. So this is one property that is important for that reason, but also through my talk as well. So that's L of gamma. So having these two general constructions, there's a natural question that you can ask, and this is really a central problem on two factors, that is to try to classify L of gamma and L infinity over x cross gamma in terms of the original group and action. So you'd like to understand, well, how does L of gamma depend on gamma? If you're given, say, a collection of groups, can you tell their group von Neumann algebras apart? Okay, so that's the motivating problem for my talk as well. I will here focus on the case of L of gamma, and I'll say a few words at the end about L infinity of x cross gamma as well. So, all right, so the problem here is to understand really how much of the structure of gamma is remembered by L of gamma. And perhaps the first example one can look at is that of abelian groups. So if gamma is an infinite abelian group, then L of gamma is isomorphic to the L infinity algebra of the dual of gamma with its Haar measure. This is just a consequence of the Fourier transform. And now the dual of gamma with the Haar measure, because gamma is infinite and abelian, is a standard probability space that's non-atomic. So it's isomorphic to the 0-1 interval with the Lebesgue measure. So at the end, what you get that is that L of gamma is always isomorphic to the canonical L infinity algebra. So regardless of what infinite abelian group you choose, you always end up with the same von Neumann algebra. And so this is a very simple example, but it already illustrates a main point about these algebras. In general, you shouldn't expect much of the information about the group to be retained by the von Neumann algebra. Already all infinite abelian groups give you the same von Neumann algebra. All right, this is also, of course, a trivial example, because when you do classification of objects, you want to focus on simple objects. So from now on, I'll be focusing on algebras that are called two factors. These are infinite dimensional simple von Neumann algebras, so indecomposable von Neumann algebras, that moreover admit a trace, like our L of gamma and L infinity of x cross gamma do. So, so in this context, you can say exactly when L of gamma is a factor or a two factor. So L of gamma is a two factor exactly when gamma has infinite conjugacy classes. So this is a condition abbreviated ICC, and it means that the conjugacy class of any non-trivial element of gamma is infinite. For L infinity of x cross gamma, we have two conditions that are sufficient to imply that factoriality. So those are being free and ergodic. So L infinity of x cross gamma is a two factor whenever the action is free and ergodic. All right, so so from now on, because of this fact, for L of gamma, all the groups that I'll consider will be ICC. So the classification problem that I mentioned here, at least regarding L of gamma, goes back to the original work of Murray and von Neumann, who were able to prove a series of interesting facts. So they proved, for instance, that there exists a unique approximately finite dimensional two factor, which they denoted by R. So what does it mean to be approximately finite dimensional? Well, this simply means that there is an increasing sequence of finite dimensional subalgebras, which is dense in your factor. So for instance, R can be represented as the closure in the weak operator topology over certain representation of the infinite tensor product of 2x2 matrices. Okay, the other fact that they showed is that if you look at the group S infinity of finite permutations of the naturals, so these are permutations that only move finitely many natural numbers, then L of S infinity is isomorphic to R. It's isomorphic to the approximately finite dimensional factor R. And finally, they also showed that the von Neumann algebra of the free group on two generators, L of F2, is not isomorphic to R. So L of F2 is a two factor because F2 is ICC, which is not isomorphic to R. So in particular, this gives you two examples, the first two examples of countable groups, S infinity and F2, which have non-isomorphic von Neumann algebras. All right, so one thing that I want to note here is the second fact that shows that for certain groups, like S infinity, L of S infinity is isomorphic to R. And it turns out that this holds in much greater generality. And in fact, it characterizes when the group gamma is amenable. So this is the next thing I want to tell you about. But maybe before I do that, let me ask if there's any questions or comments so far. All right, if not, let me go ahead and recall the definition of amenability. So this is a notion also due to von Neumann. So group gamma, a countable group gamma is amenable if its left regular representation has almost invariant vectors. This means that there is a sequence of unit vectors psi n in little L2 of gamma, such that asymptotically UG applied to psi n is equal to psi n. And examples of amenable groups include abelian and more generally solvable groups. So in particular, the integers, the group of integers Z is an amenable group. So for instance, you can see that by looking at the characteristic function of the set 1 through n, which you divide by square root of n to get a unit vector in little L2 of Z. And you can see right away that as n goes to infinity, these vectors are almost invariant simply because the set 1 through n is almost invariant under left translations with integers as n goes to infinity. Okay, and almost invariance here of the set really means with respect to its size. All right, so here's what Cohn proved. So in 1975, he proved that if you start with an ICC amenable group gamma, then L of gamma is isomorphic to the hyperfinite one factor, to the approximately finite one factor. And the same is true for L infinity of x cross gamma for every free ergodic action of an infinite amenable group gamma. So in other words, if the groups gamma that you use here to get one factors are amenable, then you always get the same von Neumann algebra R. Now, okay, and I'll sort of put this here. So this is really a remarkable absence of rigidity. It tells you that any algebraic property of the group is lost when you pass to von Neumann algebras. So if you look at L of gamma, then the only thing this algebra remembers about an amenable group gamma is the fact that the group is amenable. There's nothing else retained from the structure of gamma. So Cohn proved the more general theorem I once stated here, which classifies all amenable to one factors. And a consequence of that is also the remarkable fact that every infinite dimensional subfactor R0 of R is isomorphic to R. Okay, so R, as I mentioned before, can be viewed as disclosure of infinite tensor product of 2x2 matrices. Well, it turns out that any subalgebra of that's infinite dimensional and without center is also a copy of this closed matrix algebra, infinite matrix algebra. So in some sense, you can tell that you can say that R has some sort of self-replicating structure that's trivial in some sense. All of its subalgebras look like itself. However, it's an amazing discovery of Van Jones from the early 80s, who sadly passed away earlier this month. That if you look, however, at subfactor inclusions of R0 into R, these have a rich structure. Okay, and this is the beginning of Jones's theory of subfactors. I won't say more about this, but I thought I mentioned it. This fits well with Cohn's theorem as well. So for the rest of my talk, because of this theorem of Cohn, I'll be focusing on the opposite direction of non-amenable groups, because we know amenable groups always give you essentially the same von Neumann algebra. And so what are some examples of non-amenable groups? So the free group on two generators is non-amenable. This was already known to von Neumann when he defined the notion. Also, any group containing F2 is non-amenable because amenability passes to subgroups. And other examples of non-amenable groups include infinite property T groups. And I'll give you the definition of this notion since it plays a role later in my talk. So a countable group gamma has Kazhdan's property T if any unitary representation of gamma with almost invariant vectors has non-zero invariant vectors. Here, having almost invariant vectors is exactly in the sense I mentioned before for amenability. So there's a sequence of vectors in your Hilbert space such that when you apply the unitary representation, these will be asymptotically fixed. So Kazhdan's property T is a very strong representation theoretic property for groups, but it is satisfied by many groups, including lattices in higher rank simple Lie groups, such as SL and Z with n at least 3. So these are the classical examples of property T groups. So again, my goal here is to tell you a little bit about results concerning the classification of L of gamma. So let me mention some of the early work on this. So early, but excluding Cohns theorem that I already mentioned. So in 69, McDuff was able to show the existence of an uncountable family of group von Neumann algebras that are non-isomorphic. Okay, and this was the first continuum of non-isomorphic 2-1 factors. And in the 80s, Cohn and Jones proved that property T, which is a property of groups, is actually an invariant of L of gamma. So there's a way to define property T for the Neumann algebras such that L of gamma has property T if and only if gamma does. And in the late 80s, Cowling and Hagrup proved that if you have two lattices in SP1n and SP1m for two different positive integers n and m, then L of gamma is not isomorphic to L of lambda. So in some sense, the n here is an invariant of the lattice. So these are some of the early classification results or rigidity results. And I should say that the problem of classifying group von Neumann algebras or group measure space algebras was really intractable for a very long time. So there's been a lot of progress since the early 2000s due to Poppa's deformation rigidity theory. And the rest of my talk will concern results that were obtained using mostly these techniques. But let me just say here that this has led to rigidity results. So what are these? These are results where you can show that certain properties of groups can be recovered from the von Neumann algebras. So Cohns theorem tells you that for amenable groups, you cannot recover any information from the von Neumann algebra, whereas Poppa's deformation rigidity theory allows you to say that in certain cases, properties of the groups and actions can be recovered from the von Neumann algebra. So, so this will be the focus of my talk from now on. And so before I tell you some of these rigidity results and how they fit in the general picture, let me mention that typically many of the rigidity results are obtained as a consequence of structural results. They're obtained as a consequence of results proving something about the structure of the von Neumann algebras. And one important structural property is that of primeness. So a 2-1 factor is called prime if it's not the tensor product of two other 2-1 factors, M1 and M2. Okay, so this may, so this is the notion of primeness. You cannot write M as a product, as a tensor product of two 2-1 factors. So you may wonder, how do these tensor product decompositions arise? Well, if gamma is the product of two groups, then L of gamma is the tensor product of L of gamma 1 with L of gamma 2. Okay, so what this means is that if you can prove that L of gamma is prime, then you've strengthened the condition that gamma is not a product of groups. Okay, so this is a strictly stronger condition, but you can think of it as that. L of gamma being prime means that gamma is not a product of groups, but much more than that. So there are now quite a few classes of groups for which L of gamma has been shown to be prime. So let me mention a few of those. So L of gamma is a prime to one factor for the following groups gamma. So in 96, Ge proved that L of gamma is prime if gamma is a free group on at least n generators, and this uses Voiculescu's free probability theory. And this was the first example of a countable group gamma such that L of gamma is a prime to one factor. A few years later, Ozawa vastly generalized this result by showing that the same is true for any ICC hyperbolic group gamma, and this includes the free group, so it generalizes Ge's result. But moreover, Ozawa proved that L of gamma is solid. So what this means is that for any diffuse von Neumann subalgebra A of L of gamma, diffuse here means that you do not have a finite dimensional part. The relative commutant of A in L of gamma is amenable, and I haven't defined this, but amenable should be understood here as being small, being, well, approximately finite dimensional. So that's what was our proved, and then a few years later, Peterson proved that the same holds. So Primeness also holds for the Neumann algebras of any ICC group that has a positive first L2 Betti number. So this includes the free product of any two infinite groups and many more other examples. And the same year in 2006, Popa proved that provided a new approach to solidity of the free group factors. So to Ozawa's result for free group factors based on deformation rigidity theory. And there's been many other classes since then. I will just mention one of the latest results from last year, and this is due to Isono and Marachi. So they proved that if you look at any reproduct group, gamma, which is the reproduct of sigma with lambda, so sigma, so this is defined as you look at the infinite direct sum of sigma, copies of sigma indexed over the group lambda. Lambda acts on the index set lambda by left translation, so you can form the semi-direct product, and that is the reproduct of sigma with lambda. Isono and Marachi proved that L of gamma is prime whenever sigma is a non-trivial group and lambda is non-amenable. All right, so there's lots of classes of groups for which we know that L of gamma is prime, but there is one natural class for which this is largely open. So let me put that as an open problem. So it's an open problem to prove that the von Neumann algebra of SL3Z and more generally of PSLM Z with M at least 3 is prime. More generally, you'd want to prove that L of gamma is prime for any ICC irreducible lattice in a semi-simple Lie group, so in a product of simple Lie groups. And I should mention what I mean by an irreducible lattice. So as usual, a discrete subgroup of a locally compact group G is a lattice if it has finite covolume. So there's a finite volume, a fundamental domain for gamma. And a lattice in a product of groups is irreducible if its projection onto a subproduct, where you take out one of the factors, is always dense. And I should mention that, so this is still an open problem in its generality. However, a few years ago, with Daniel Drimbe and Daniel Hoff, we were able to settle this problem under the assumption that all the simple Lie groups involved here, G1 through Gn, are of rank 1. So let G be the product of n simple Lie groups of rank 1, each of which is assumed connected, non-compact, and with finite center. These are usual assumptions. And let gamma be any ICC irreducible lattice. Then L of gamma is a prime to one factor. Okay, so you need to assume gamma to be an ICC irreducible lattice because you want to get a to one factor, but also if gamma is a reducible lattice, the product of two lattices, then of course L of gamma cannot be prime. All right, and in particular, this implies that the following groups, so PSL2 over the ring Z adjoin square root of 2 and the ring Z adjoin 1 over P. And here I have to tell you what D and P are. So D is a square free integer which is not congruent to 1 mod 4, and P is a prime. So both of these are prime to 1 factors. How do they follow from the theorem? Well, both of these groups can be realized as lattices. For instance, for the first group is a lattice in SL2R times itself. And the second one is a lattice in SL2R times SL2 of QP. So these are both lattices in product of two groups of rank 1. And so these are the first examples of prime to 1 factors that come from higher rank lattices, from lattices in higher rank Lie groups. So this settles the primeness problem, if you want, for for products of rank 1 Lie groups. But in this context, I should mention there's another natural open problem. So you expect for such a lattice gamma much more to be true. So it's an open problem to prove that L of gamma is solid, and in the sense of Ozawa's theorem. And there's an even more general notion of strong solidity due to Ozawa and Poppa, and that should also be true for these lattices. But at this point, even for PSL2 of Z, say square root of 2, we don't know anything about solidity or strong solidity. All right. So Dave, if I can ask, how much more time do I have?
Oh,
any
looks like
questions?
a little bit less than a half hour, so like 25 minutes.
Okay, perfect. If there's any questions, just feel free to stop me at any time. All right, so on the last couple of slides, I told you about some primeness results. So these give groups such that L of gamma is a prime to 1 factor. And let me emphasize how this ties in with our theme here of rigidity for group von Neumann algebras. So if L of gamma is prime, that, as I remarked before, gamma cannot be the product of 2 infinite groups. So in some sense, you can view this as L of gamma remembering that gamma is not a product group. It remembers that the absence of a product decomposition for gamma. And I can make this even more precise. If you know that L of gamma is prime, then for any other group lambda, such that L of gamma is isomorphic to L of lambda, lambda is also a prime group, if you want. It doesn't have a direct decomposition. All right, so this is about the absence of a product decomposition. And a related result was established by Kifan, De Santiago, and Sinclair in 2015. So here's what they showed. So let gamma be the product of n ICC hyperbolic groups. For instance, you can take gamma 1, gamma 2, gamma n to all be a free group. Then if L of gamma is isomorphic to L of lambda for some countable group lambda, then necessarily lambda is itself a product of n infinite groups. Okay, so if you take gamma to be F2 times F2, the free group on 2 generators times itself, then any other group lambda, which gives you an isomorphic von Neumann algebra, would have to also be a product group. And in fact, there's more you can say. By combining this with a result of Ozawa and Poppa from 2004, you can also deduce that L of gamma I is, well, essentially isomorphic to L of lambda I. Okay, so in other words, this result tells you that L of gamma remembers the product structure of gamma. It remembers that the group gamma you put in is a product group. This is a property that passes to any other group, giving you an isomorphic von Neumann algebra. Okay, this is really in contrast with amenable groups. You can have, S infinity, which is not a product group, gives you the same von Neumann algebra as S infinity times itself. Okay, so what we've seen so far is that sometimes L of gamma remembers the absence of a product decomposition, and sometimes it remembers a product decomposition. So it's natural to ask what other group theoretic constructions you can recognize at the level of the von Neumann algebras. And I'll tell you one more result in this vein. So this is due to Kifan and myself from 3 years ago. So for a class of amalgamated free product groups, so gamma is an amalgam of gamma 1 with gamma 2 over a common subgroup sigma, we have the following. Well, if L of gamma is isomorphic to L of lambda for any group lambda, then lambda itself has to be an amalgamated free product. Okay, so of course you have to avoid the fact that I could be taking a trivial amalgam here, so there's more to it, and moreover, if you want, the components of the amalgam give you isomorphic von Neumann algebras. So L of gamma 1 is isomorphic to L of lambda 1 and so on. Okay, so in other words, you can say here that L of gamma remembers that gamma, the group gamma, was an amalgamated free product group. All right, so I'm not stating this theorem with precisely for a reason, because obviously this won't hold for all amalgamated free products. You have to take very special ones. But let me mention one class of groups to which it applies. So it applies in particular to the following groups. So you take any ICC amenable group A, such as S infinity, and you take any ICC hyperbolic group B. And then what you do, well, gamma 1 will be the direct product of A free product B with itself. And gamma 2 will be the same group. These two groups contain natural copies of the direct product of A with itself, and that's the subgroup over which you amalgamate. So products like this, which there are uncountably many of, satisfy this rigidity theorem. All right, so so to recap all of this, we've seen now several properties that are remembered by can be remembered by the von Neumann algebra: amalgamated free product decompositions or product decompositions. But of course, the ultimate type of results here would be to recover the whole group. Okay, so you'd want groups for which you can recover not only specific properties, but the whole group structure. So you'd want to recover the isomorphism class of the groups. So, so this is called superrigidity. So a countable group is called Wstar superrigid. So here Wstar stands for the Neumann algebra. If any group lambda, which satisfies that L of gamma is isomorphic to L of lambda, must be isomorphic to gamma. Okay, so in other words, there's no other group lambda other than itself. So there's no group lambda other than gamma, which gives you an isomorphic von Neumann algebra. So this is in a very strong sense saying that L of gamma remembers the isomorphism class of gamma. And so let me mention the first results of this kind were found by Popa, Vas, and myself 10 years ago. So here's what we showed. So maybe I can give you the conclusion. So we showed that a certain generalized Reef product group is superrigid, is Wstar superrigid. And it's a generalized Reef product group of the following form. So you have a group G acting on the direct sum of zima 2z's index over an infinite set I on which G acts. So this is how you build the general Reef product group. And so I have to tell you what G and I are. Well, these are constructed from any non-amenable group G0 and any infinite amenable group S. You look at the Reef product G naught with S, and then you take the action on the coset space G mod S. Okay, so it's a two-step construction. First, you build this action of G on I by using a Reef product construction, and then you build a generalized Reef product group. So it's an iterated generalized Reef product group. So it's it's a fairly complicated construction, and there's a reason why it's this complicated. So for plain Reef product groups, Popa had proved earlier that you have the following rigidity theorem. So if you have two Reef product groups where you take zima 2z, the group on two elements, Reef product with G, and if this is isomorphic to another such Reef product, then you must have the G is isomorphic to H, provided the G and H are ICC and have property T. Okay, so if you're looking at plane reef product groups of this kind, where there's no generalized, so there's no action on a set I, then you have this rigidity theorem. However, plane reef product groups are never super rigid. And this is why in our theorem we couldn't prove superrigidity for such groups, because if you have any plane reef product group, and if, for instance, G is torsion-free, then you can always find a torsion-free group lambda such that L of gamma is isomorphic to L of lambda. And now lambda is torsion-free, but gamma definitely has torsion from zima to z. So gamma and lambda cannot be isomorphic. All right, so so these are the first examples of superrigid groups, and after that, there's a couple more works providing more examples. So Berbeck and Vass in 2012 proved that you can look at what's called a left-right reef product group, where you take an ICC hyperbolic group gamma, and you form a reef product of this kind, where gamma acts both on the left and on the right by multiplication on itself. And also with Ionutsky-Fan, we gave examples of W-star superrigid groups that are amalgamated free product groups. So, so this really summarizes the known examples of superrigid groups. And along this line, there's an old conjecture of Cohn that predicts that, in fact, all property T groups should be superrigid. So let me mention that. This is Cohns' rigidity conjecture from 1980. So it says that if gamma and lambda are ICC property T groups, and L of gamma is isomorphic to L of lambda, then gamma should be isomorphic to lambda. Okay, so in other words, within the class of property T groups, isomorphism of a Neumann algebra should imply isomorphism of groups. But now you remember that Cohn and Jones proved that property T is a property of the von Neumann algebras. So if gamma has property T, then so does L of gamma, so does L of lambda through isomorphism, and lambda has to have it as well. So it means that in this statement, it's sufficient to assume that one of the groups has property T. So in other words, Cohn's conjecture is equivalent to asking whether any ICC property T group is W-star superrigid. So this is a wide open conjecture. We know very little about it. And I should mention two sub-problems here that are open. So first is an outstanding open problem asking to prove that if you look at SL and Z, and I'm taking here PSL and Z to get an ICC group, but if you look at PSL and Z with N and M at least 3 and different, then the problem is to show that PSLM and PSLM give you non-isomorphic von Neumann algebras. And this is still open. Let me mention here that a couple of years ago, in joint work with Rémi Boutonnet and Jesse Peterson, we introduced a new method to study von Neumann algebras of PSLM-Z. And with it, we couldn't attack this problem, but we could prove some indecomposability results for the von Neumann algebras of SL3Z, for instance. So we could show that they're never isomorphic to a cross-product algebra or a group measure spaces algebra coming from a weakly compact action. Okay, so we could rule out some decompositions for PSL and Z and for N at least 3. And the second open problem here, so this has to do with the equivalent formulation of Cohn's rigidity conjecture. So this says that this predicts that any ICC property T group should be W-star superrigid. Well, as of now, there's no example of W-star superrigid property T group. So even finding one example which confirms this this equivalent formulation of Cohn's rigidity conjecture is of interest. All right, so so this is Cohn's rigidity conjecture and related open problems. So I should not end this slide before telling you the sort of the counterpart of this problem for the free groups, which is the famous free group factor problem. So the free group factor problem, which motivated Voiculescu to start free probability theory is asking whether for two free groups, Fn and Fm of different ranks, you have that L of Fn is isomorphic to L of Fm. So this is also one of the outstanding open problems on group von Neumann algebras. So this is all I had to tell you about group von Neumann algebras. So I finished with this conjecture of Cohn and the free group factor problem. And I have one more slide to show you, which is about group measure space algebras. So what I want to tell you there is that in contrast to group von Neumann algebras, a lot more is known there. So that's a different and much longer story that I don't have time to tell, but let me just mention two results here, which in some sense you can view as group measure space analogs of this Cohn rigidity conjecture and free group factor problem. So these are from about 10 years ago. So first is a result of mine from 2010. So take gamma to be any ICC property T group, for instance, SL3Z, and take gamma on X to be the Bernoulli action of gamma. So for instance, I can take this to be the action on gamma on 0, 1 to the power gamma, where 0, 1 is endowed with the Lebesgue measure, and G, a group element G acts on a sequence of elements in 0, 1, of numbers between 0 and 1, XH, by just acting on the index set. So G applied to X gives you a new such element where you translate the components according to the left multiplication action of G on gamma. So these are free ergodic actions. And what I proved was that any such action is super rigid is Wstar super rigid in a sense analogous to the notion for group von Neumann algebra. So precisely, if you have any free ergodic action of any countable group lambda, which gives you an isomorphic von Neumann algebra, then the groups gamma and lambda have to be isomorphic, and the actions have to be isomorphic. Okay, so this is saying that in the strongest possible sense, L infinity of X cross gamma remembers the group and the action it came from. So this relates to property T groups. And a couple of years after this, Popa and Vass proved the following analog of the free group factor problem for group measure space factors. So they proved that if you have two free groups of different ranks, N and M, and you take any free ergodic actions of them, then the group measure space algebras L infinity of X cross Fn and L infinity of Y cross Fm are never isomorphic. So somehow, although it's still open whether L of Fn remembers the rank N, this is the case for the group measure space case. And I think I'll stop here. Thank you for listening.
All right, thank you so much, Adrian, for that wonderful talk. Perhaps we will stop the recording now and allow people to ask questions.